Oh, hello there. I'm a chaostician. You don't know what that is? Well, in short, I study chaos theory. You don't know what that is either? Allow me to explain. Take a dino, for example. If it were to sit on top of a roof and lay an egg, which way would it roll off? Seems like both ways are an acceptable answer, and you're right. That's chaos theory. However, it's more complicated than that. Chaos theory defines the immeasurable. You can't model chaotic systems with the laws of classical mechanics like Newton's 3 laws of motion. By their very nature, chaotic systems are erratic, seemingly unpredictable, and any slight difference in their initial conditions causes a spiral into chaos. Here, let me show you. This is a single pendulum. It represents a normal system. It sways back and forth, hinging on one point. Its velocity and motion can be modeled in an equation, and its direction can be predicted. When I drop two single pendulums from different positions, each takes a regular predictable pattern of motion. They are not sensitive to initial conditions. But if I drop two double pendulums, they quickly separate, taking unique paths of chaotic motion. By introducing just one more hinging point, the velocity, acceleration, and movement of the pendulum are all highly sensitive to initial conditions. The movement of the double pendulum seems completely unpredictable, but biologist Robert May actually found a way to model chaotic systems. May initially developed this equation to model population growth and predict where a population will reach equilibrium. So for a population of, say, dinos, this is the predicted population, and this is the current population. In the equation, xn is multiplied by r, the population's growth rate. Of course, this by itself models an exponentially growing population, but it can't grow forever because of limitations in the environment. So it must be multiplied by this, which places a limit on population growth. When graphed, this is an inverted parabola which peaks and returns to 0. In other words, too many dinos now, fewer in the future. They're self-regulating. Phew! But here's where it gets really interesting. If the x-axis is the population's growth rate and the y-axis is the equilibrium population, which remember is the number where the population theoretically stabilizes, then we get a steadily growing graph, but only for a while. Once it reaches a certain x value, it splits in two. This is known as a bifurcation. At this rate of growth, the population oscillates between two equilibrium points. In one year, the population is higher, and in the next year, it is lower. As the graph continues, it splits into 4, then 8, then 16 different population points, and continues to split until the graph reaches chaos and the population never settles on a single point of equilibrium. The graph seems chaotic, but there are spaces in which the erratic pattern is more steady. Scientists found that, if they graphed extremely irregular heartbeats known as fibrillation, they could identify the more steady bifurcations in the pulse and send electrical shocks to the heart. These shocks decrease the oscillation between values, bringing the heart rate down to a steady, normal pulse. In short, the scientists used chaos theory to tame the chaotic beat of the heart and save it from stopping. Chaos can seem daunting, but as you can see, familiarity and innovation emerge from the unpredictable. And now the dinosaur is roaring. Nobody could have predicted that. That's chaos.